Hello, I'm Hugh Manfield, and welcome to the first lecture on fluid space theory. Now, before I can dive right into fluid space theory and how it works, I have to do some groundwork and establish some things. We need to learn about reference frames and motions within those reference frames, and we need to learn about Newton's laws and Einstein's special relativity. And once I've covered those topics, then we can go into fluid space theory and see how it actually works. If you're interested in learning more about it, I've written everything in a book called Einstein and Aliens, and subtitle, A New Approach to General Relativity. The book includes appendices in the back that contain all the math and the logical derivations, and the first half of the book is a science fiction story, so if you don't want to do all the math, you can just read the story and learn about fluid space theory that way. In keeping with my approach of keeping things simple, I'm going to start with the two basic reference frames. Now, what is a reference frame? A reference frame is something where we can put coordinates on it. That way we can map out the contents. For instance, if we put coordinates on this box, we can map out the contents of the box and the location of objects and track their motions. There's two basic types of reference frames. First of all, there's the inertial reference frame. We see on the side A of the chart, and that's where you feel weightless. You're floating free like an astronaut in space, on the space station or out in space, away from any massive body, and you're basically in free fall. That's an inertial reference frame. Now on the second side of the chart, in side B, we've applied a force to the box. And we have Ricky in the box and Stan outside watching what's happening. So when the force is applied, the box begins to accelerate along the direction of the force. And all the objects in the box are collected on the floor, and then the floor applies force to them and they go along with the box. So Stan sees the box accelerating through space away from him, while Ricky inside the box feels the sensation of gravity. So this is an accelerated reference frame. When you feel weightless, you're in an inertial reference frame. When you feel gravity, you're in an accelerated reference frame. So now we've taken the same glass box, but instead inside we have a branch of an apple tree and an apple hanging from that branch, as in Newton's apple story. And there's a force applied to the box, so it's accelerating through space, and Stan is flying alongside with his rocket pack so he can keep up. So right now, the only force acting on the apple is being transmitted through the box and the stem to the apple. So now, at the instant the stem breaks, there's no longer any force on the apple, and Stan cuts his motors. Now, Stan and the apple have entered an inertial reference frame. They don't feel gravity, they feel weightless, and there's no force acting on them. The box continues to accelerate away through space, and the apple and Stan will fall to the bottom of the box, and if there is no bottom, the apple will fall out, and Stan and the apple will track along together in parallel, and the box will zip away out into space. There are basically three ways to experience gravity. The first way is like I've just shown, linear acceleration, where you're in some sort of a box. It could be a spaceship or anything, and a force is applied to that box, and the box accelerates along in the direction of that force. So inside the box, you feel the acceleration, and the force acts on the bottom of your feet. The second way is on like a spinning wheel, like a merry-go-round or a big wheel space station. And in that case, you're going around in a circle, so there's a force on the bottom of Ricky's feet, which keeps her on the circumference of the circle as she goes around, and she feels gravity. And the third way to experience gravity is to stand on a massive body. I've cut away the rest of the body, but Stan is standing on an asteroid, and he feels weak gravity. Those are the only three ways to experience gravity, and you can combine them in various ways. You could have a spinning wheel, like at a carnival ride, on a massive body, where you experience linear and rotational accelerations, but really you can always break it down into those three things. So now we go back to Ricky in the box, floating free, but in this time, in this situation, we've applied the force to Stan. So now Stan is going to accelerate upward through space, and from Stan's point of view, Ricky and the box are falling away below. So now that's what's going on if you were out in space. But what's going on the surface of the Earth? Well, it's the exact same thing. If we put Stan on a tall tower above a planet, and you can see the horizon, now there's a force acting on his feet, accelerating him upward through space, and he sees Ricky in the box fall past. It's the exact same thing that's going on. And to make this, try to make this a little clearer, I've invented a rocket-powered football field. Now right now the rockets are off, so anyone on the field or in the dome would feel weightless. It's an inertial reference frame. And we have a ball on about the 15-yard line. If someone throws the ball while it's in an inertial reference frame, the ball will move in a straight line at a constant velocity. I've charted that out on this graph. Now, let's say that at the instant the ball is thrown, we light the rockets on the football field. Now the football field will start to move upward, and I've charted where that is on these green lines: 1 second, 2 seconds, 3 seconds, 4, 5, and 6. And what we see is that at 1 second, the field is still below the ball, so we plotted that up here. At 2 seconds, the field is even further below the ball, so we plotted that up here, so the ball is continuing to rise. At 3 seconds, the ball and the field are moving at the same speed, so the ball begins to follow this path. At 4 seconds, the ball is getting closer, it's starting to come back down. At 5 seconds, it's getting even closer, and at 6 seconds, the ball arrives at the surface of the field. So, from the point of view outside the stadium, the ball moves in a straight line at a constant velocity, but from the point of view of someone on the field, while the rockets are firing, the ball follows a curve. So now let's think about that a little bit more. Let's start and let's let the quarterback throw the ball while the rockets are off. And we'll let it run for 4 or 5 seconds, and the ball will move in a straight line at a constant velocity. Now we light the rockets, and from the point of view of the field, the ball will start to move in an arc and fall down toward the field. So, from the point of view of the field, it would appear that there's some sort of gravitational field acting on the ball to pull it down to the field. But that's not what's really happening. What's really happening is that the field is accelerating upward, it's gaining more velocity, it catches up to the ball, and the ball appears to move in a curve, but in reality, the ball is in an inertial reference frame, no force has acted on it, and it continues to move in a straight line at a constant velocity. And you would see that if you were on the outside of the stadium floating free and you watch the stadium accelerate upward and catch up with the ball. So the same thing is happening on the Earth. Let's bring that stadium down to the Earth, or I'll just show it in this chart. Once again, Stan is being dragged upward by a force, and he sees inertial reference frames falling past, downward. Okay, now Stan's standing on a tower over a planet. The force is acting on his feet, forcing him upward, and relative to the inertial reference frames, which are falling downward to the surface of the planet. So this is what's actually going on with gravity, but it's kind of hard to reconcile, because if you think about it, the Earth is round. So if inertial reference frames are falling into it, they have to be falling in from every direction around it, and it would seem like there's really no place for them to go. But fluid space theory can explain this, and this is where it starts to get really interesting. So now that you understand that gravity is nothing more than an acceleration field in space, you're ready to take the next step and learn more about space, time, and relativity. That's going to be in my next video. Now, these videos may help more if you watch them in sequence, so check out the playlist down below and send me a comment if anything was unclear. Or you can suggest a topic for a Keeping Science Simple video on my other channel, and I'll consider making one to help explain a topic to you. Until then, I'm Hugh Manfield.